everyone. My name is Kelly Hall. I'm a marketing coordinator here for ALS North America. I want to thank everyone for joining us today on our Webinar Wednesday series. Our presenter today is Michael Holloway. Michael holds a BS degree in chemistry, a BA in philosophy, and a Master of Science in engineering. He has over 30 years of experience in research and development, technical marketing, equipment reliability, and sales, along with publishing numerous books on these subjects. Michael is a certified lubrication specialist, oil monitoring analyst through STLE, a level 1 machinery lubrication technician, and a machinery lubrication analyst through ICML. Now Michael serves as a manager of strategic accounts and external training at our ALS Houston laboratory. And today, Michael is going to be discussing failure modes of lubricated systems. During this presentation, feel free to use your chat box or ask a question feature or your raise the hand, and we can go ahead and ask Michael questions throughout this presentation. Michael, thank you again for taking your time to deliver this presentation today. I will go ahead and turn it over to you.
Great, thank you very much. I just want to make sure that you can see the screen that says failure modes of lubricated systems.
Yes, everything looks great.
Okay, great. Excellent. Well, thank you very much for attending today's webinar. You know, for some of you, it's right after lunch. Maybe it's right during lunch and right before lunch. So, as Kelly said, feel free to ask questions, and we'll do the best we can to answer them. Okay. Now, what I'm trying to do is advance my slide, which isn't advancing. A bit of an issue, Kelly. Oh, here we go. Got it. For whatever reason, the keyboard wasn't working very well. Okay, so for today's webinar, we're going to first look at the objectives of what we're trying to do. First and foremost, let's define our terms in defining failure. Then we're going to identify various sources of failure. And then, obviously, explore wear mechanisms, contamination, and oil condition change. Well, those are going to be all different types of ways in which these lubricated systems can fail. Some of these you'll be very familiar with, others, hopefully, it'll be new insight. Now, failure, it's defined typically, depending upon who you talk to, as any loss that interrupts the continuity of production or a loss of the asset availability or not meeting expected targets. But whatever failures, however you define it, the bottom line is when something fails, it no longer is doing what you've intended it to do. And really what we're trying to do is, first of all, figure out why that occurred. Because in doing so, we can then figure out how to make it not occur as often or maybe not even not at all going forward. Now, not surprisingly, top 20% of all failure events represent 80% of economic losses for a facility. That's a typical Pareto curve. And there's a Italian mathematician who developed the Pareto curve. The last name was Pareto, actually. And he came up with the concept of the significant few. And really, it does boil down to many things. In fact, we know this in business that perhaps 80% of our business is really attributed to 20% of our customers. Now, the same can be said for failure modes. About 80% of the economic losses that any facility experiences is typically attributed to 20% of those failure modes at the top end. So if we can just focus on those things, a lot more savings can be realized. Now, when we do talk about failure, obviously various things are affected. When things fail, obviously we're going to have to replace the parts. We're going to have to throw labor at it to fix. And that asset is obviously experiencing downtime. So it's not doing the intended job it's supposed to be doing. All these things cost money. Parts replacement, labor cost, and downtime is money. There's also other types of money that's involved as well. Maybe additional services. Perhaps an outside contractor has to come in and fix something. Maybe we have to buy additional capital or at least lease it. And that's going to take resources and money. And obviously product is affected as well. A lot of times if we do have to change over to a new production machine or whatever, productivity can be waned, but also the product itself may suffer. And there's probably associated, according to whatever business you're in, whatever vertical, there could be other types of costs that are associated to the cost of failure as well. Now, there's all different reasons why things fail, but really, if we boiled it down, we can actually discover that it really does just come down to a few things. Maintenance is in place to address failure, whether it's fixing failure, helping us avoid failure, maybe determining what the failure is if we don't have a reliability assurance department. And sometimes we can actually predict failure. We're really looking to minimize or eliminate. But if we boil all failure down, we can always pinpoint it to either a methodology of failure, the failure of a person, the machine itself failed, or a material failed. For us, material failure will be something we'll focus on, because in this case, we're actually talking perhaps about the metallurgy failing or the oil or grease failing, and for a number of different reasons. Now, with that, obviously comes methodology, man and machine, and often material can fail, but also the methodology around how that is actually being applied and dealt with can fail as well. So like any other failure opportunity, there's always more than one reason why something fails. Often there's a primary and several secondary. Now, when we actually go and purchase a particular machine, we're spending money on it, and over on this particular graph here, we see on the y-axis is the profits or money, and then on the x-axis, the horizontal axis, that's time. Well, the first level here is the economic life of that particular machine. So that's amortization. So we bought something, and over a period of time, it's doing the job and it's actually making us money, but we're paying off the debt of that asset. And over a period of time, it does pay for itself. It isn't until we get past that and go into what's called a profit life do we actually start experiencing some serious profitability. That's the margins. But at some point, we hit a level where we actually start going beyond its profit life, and we're starting to throw maintenance at it, and it goes into its physical life, into its very termination. Now, we can extend out the profit life by extending out the reliability. And the way to extend out reliability is to address failure and understand, first of all, where it's from, and secondly, how we can eliminate it or at least reduce it dramatically. Now, there's various different ways to actually we can define failure. I'm sure that many of you have seen these kinds of graphs before. The most common one is the first one. It's called it the bathtub curve. That's age-related. And we'll go into a little detail about this here in a minute, but there's several other patterns as well that are pretty well defined. Depending upon the machine, the method, the process that's underhand, it really does depend upon what kind of curve it's being addressed. Now, at the very beginning, we call this the infant mortality. This is at the very beginning of a particular asset. It's got a very high incident of failure. And we're going to explore a few different reasons why this is. But as soon as those things get shaken out during its mid-phase, it's running quite reliable. It isn't until the very end of its life, age-related failure, does it terminate. Now, one way we can actually understand failure and how to actually use it is by utilizing a failure mode effect analysis, FMEA. It's a systemized group of activities. It's designed to, first of all, recognize and evaluate these potential failures, the product or process, and then we're going to identify the various actions which could actually eliminate, if not reduce, that failure, and then document the process. Now, we won't spend a whole lot of time on FMEA. That's a whole other webinar. But needless to say, it's a very valuable tool and very powerful tool as well to increase reliability and increase productivity and profitability as well by reduces failure, reduces downtime. Now, when someone fails or breaks, it's doing so because of a particular change. And that change could be wear, where things are actually wearing out, all right? Could be due to, oops, sorry, I want to go back. Could be due to fracture, parts breaking, or molecular transition. And that could mean anything from metal oxidizing to it actually breaking up crystallinity, or it actually becomes a deformed. Okay, some sort of deformation occurs due to changes occurring, wearing, fracturing, molecular transition, and deformation. I'm kind of hard pressed to figure out if anything falls outside of those four realms of change. Now, after change, there's an influence on that environmental condition that makes change occur. It could be force, temperature, time, or even chemical. When we think about force, it comes down to thinking about how the machine is operating in its given process. It's designed to do something, but if for whatever reason the productivity requires increased, you're actually going to be increasing force and componentry, it's going to break. Temperature can work the same way. Obviously, the more we run a machine, the hotter it's going to get. That increases temperature, and with temperature brings about a whole host of other problems. Time, not letting things obviously cool down or whatever, is an influence, and chemical influences. Anything from a washed down chemical to a processed chemical, all the way down to maybe a lubricant breaking down for certain reasons. Now, all these influences have a cadence. We call it a particular rhythm. And that could actually be associated to variations in articulation, amplitude being strong or weak, or even frequency being fast or slow. Sometimes, if you can think about a jackhammer versus the vibration of a plant floor, both can be very dangerous, but obviously a jackhammer is going to produce a strong amplitude and a fast frequency, whereas perhaps the plant floor produces a very weak amplitude and maybe a very slow frequency, but it still could vibrate the very parts that might be lying in stores of the crib and create some false Bernelling even. There's also going to be, it could be steady, it could be random, and it could be cyclical. And all these things are really important to understand how they, what brings about the influence of the change. Now, with that comes an effect, an effect, but an affect. And that affect can work on the componentry from the surface and work inward, or that particular part and component can actually break from the inside out, or all at once. And this is important because, once again, we say, well, a part's going to break, it's going to break, it's going to break. But if we can actually understand the effect of what's going on and do a little analysis to understand what caused this, we might be able to set up a preventative measure so it doesn't occur again. Now, here's just a cascade of events from the change to the influence, from the influence to the cadence, from the cadence to the articulation, and on through to the affect. Now I'll give you an example right here. Here's a pump impeller. Okay, and maybe a few of you have seen something like this in the past. If you haven't, it's a little prop on the inside. Okay, it's going to obviously convey a fluid from one spot to another down the line. Pumps are probably one of the very first real machines beyond a wheel that human beings invented that would really propel us into a whole different world, because now we're able to actually move water back thousands of years ago. And they were first pumps were developed many thousands of years ago, actually. Changed everything. If we didn't have pumps in our factories, we wouldn't have factories. That's the bottom line. So they are important. So I use this as an example. Now, let's say it fails. Okay, the pump fails. Well, I'm going to start asking questions. Why did the pump fail? Because the impeller failed. Okay, well, why did the impeller fail? Well, because it became adrift. Now, we got to keep on asking why till we get to the final answer, till we can't ask why anymore. Well, why did it become adrift? Because the mounting nut came undone. All right, why did it become undone? This can be a real pain in the neck for the interviewer, because a person on the receiving end seems like you're talking to a 4-year-old. But the most amazing thing is that you do get to the bitter crux of the matter when you keep on asking why. Well, that nut came undone because it wasn't properly torqued down. It was an assembly error. It comes right back down to perhaps methodology. Maybe the assembly technician wasn't taught proper on how to torque it down, or maybe he just failed because he was having a bad day or she was having a bad night or something like that. Or perhaps there was a failure of the material in the thread, who knows? But the bottom line now is it was attributed to assembly error. You see, we're never going to be able to get to the understanding of failure unless we ask why, until we ask why to the nth degree. Normally it takes between 4 and 6 whys before we really get to the true answer. If we ever get to the point where I don't know, then we're not actually analyzing it enough and looking down deep into it. Now, there's a graph on the probability of failure. If you notice on the y-axis, the probability of failure, the higher it goes, the more probability. And the x-axis, the time, that's the service age. Now, this is our bathtub curve. We have early failures, random failures, and time condition failures. Now, we're going to explore early failures here in a minute, and then obviously the random failures is what happens throughout the life of that machine until we get to the time-based or condition-based failures. When we look at the early failures, there could be several different reasons why these things are occurring. Inadequate lubrication usually happens. Perhaps we're putting the wrong grease, the wrong oil in that asset. Viscosity is the #1 characteristic that has to be considered when we're lubricating the machine. Improper viscosity is definitely going to have a huge influence on early failures. Poor installation, obviously, not so much a lubricant issue, but still an issue nonetheless. Wrong components and materials, and that also includes oil and grease. New component defects. Usually call this the burn-in phase. Usually when things are brand new, they do go through a burn-in phase before all the issues get shaken out. And then poor maintenance practices of workmanship. We get into random failures. There's a couple different types of that. There's instantaneous random failures. Once again, that's attributed to manufacturing defects, material defects, metallurgy is wrong, improper maintenance as well. Perhaps during the whole the commissioning process worked fine, but the overall maintainability of that asset was lax. Loss of lubrication. Perhaps things just aren't greased as appropriately, or the oil's not changed out, or production calls for more productivity out of that asset, so that it actually experiences an overspeed and overload environment. All these things are random, but they're instantaneous, and that could attribute to that failure mode. The other thing is, on random failures, we could be event dependent, and that's usually event-dependent failures are really initiated by engineering, maintenance, or operations management. Things change. Normally, if they're in a particular routine, everything's running well, then all of a sudden a change notice is put into place without real good analytics behind it, and that brings about an event-dependent failure. Sometimes it's accidental, but usually it's related to a lack of knowledge or management oversight. And then on the end, the time-dependent failures, when things reach their end of life. And that occurs at the end of equipment component life cycle, and this is usually due to thermal cycling or fatigue cycles. At one point, just it gets to be too much. It's not going to last forever. And it's important to understand the equipment components life cycle as well. In a more advanced class, we'll talk about the L10. But right now, this is you can always Google that and look that up. It's actually interesting. You do L10 analysis on bearings and other things as well. It gives you a good understanding of component life cycles. Then there's also condition-based failures. That's where we talk about condition-based, where it's surface deformation, contamination, it's gradual or accelerated, and lubricant degradation. Here's where oil analysis really can come into play. Now, I put added depletion in here, and really it's probably depletion isn't the best explanation. You know, when you do oil analysis and you see that you have your various organometallic componentry in there in a brand new sample, and those levels really don't change over time unless it gets diluted out or sweetened with the wrong oil, but their functionality changes. You know, if you have zinc dithiphosphate in your oil, you're always going to show up with zinc and phosphorus, but the functionality of that changes over time. The same thing maybe calcium in an engine oil. It's going to always be in there unless it's diluted out, but the functionality changes. So I guess what I'm saying is that we don't want to always think about additives depleting like they're evaporating. They're not going any place. They're just changing their functionality. The metal's always going to be in there. Now, we also have something to think about is the wear phases, because wear is attributed to probably anywhere from 70 to 75% of all failure. And it's defined as simply loss of material from one or both surfaces. Now, that can occur, obviously, during the wear rate and equipment age. It looks a lot like the bathtub curve. The break-in, normal, and abnormal are accelerated. It falls right in line with the bathtub curve we looked about earlier. So during the break-in phase, most likely, we're going to attribute a lot of wear during that break-in phase. And the only time we're actually going to see more wear is during the very end of its life cycle, is when it truly does wear out. The break-in phase typically is attributed to machining of a new component. And a lot of times when you buy a brand new asset, it's not completely clean on the inside. The metal, for whatever reason, and there's several different reasons why they don't polish completely smooth, but there's a break-in phase to this. It isn't until that actually gets worn down somewhat, that we actually see a reduction in that wear. If it's coming from internal motivated, if it's coming from an external source, that's a different story altogether. Normally, obviously, if we have normal wear during that phase, that's typically going to be attributed to a compromise of the film strength between the things. And quite frankly, normal wear occurs mostly during startup. When we're in a startup position, when that machinery is at rest and goes from rest to moving, you're going from two surfaces that are basically almost in contact with each other, and most of the time the asperities might be contacting each other, to when that lubricant film gets established. That in between is where wear occurs most often. That's really normal wear. Now, the abnormal accelerator wear, that's attributed to overtaxing the asset, but it's also attributed to contamination and eventual lubricant breakdown. We're going to talk about that here in a minute. Now, as we spoke about earlier, wear attributes itself to a vast percentage, greater than 75% of failures attributed to wear. This is these kind of numbers came back, it's interesting. There's a guy named Ribowitz, I believe that's how you pronounce it, Ribowitz out of MIT. He'd done this study back in the early 80s on understanding the usefulness of aircraft and really tried to understand why things would fail. And he came out, he's like, surface degradation is attributed about 70%, accidents about 15, obsolescence about 15. But of surface degradation, some of it was attributed to corrosion, but a lot of it was contributed to mechanical wear. And of mechanical wear, you have abrasion, fatigue, and adhesion, is that he identified. Now, there's several more types of mechanism behind wear, but it's good to note. So if we can actually maintain a film between two moving surfaces, reduce the amount of contamination, we can really reduce the amount of mechanical wear. We'll go into a little bit of detail about the various types of mechanical wear here in a second. Of all the failure modes associated to lubricated systems, wear, probably one of the bigger ones. Obviously, contaminants come into play as well. Particulate does obviously speak to wear mechanisms, and the oil condition comes back to wear as well. So by looking to control contamination, oil condition, we can actually have a good influence on wear as well. But we do have to understand where these different types of wear mechanisms and wear modes actually come from. Now, of these lubricated systems, and we looked at the different types of wear, we can have like for instance, abrasive wear. We can have a force associated to that. And this example would be cutting. Abrasive wear is attributed to a cutting particle, cuts down knee. And adhesive might be due to the force's load. And fatigue wear, it's dynamic strain. Corrosive wear and cavitation and erosion. And all these things, they obviously have a force, and the forces are different. But with the force comes a time and cadence. It could be cumulative, per revolution, contact duration, all the way down to cumulative impacts. This is where it comes back down to that cascade of events that we saw earlier, understanding time, cadence, and force. By understanding this, we're starting to understand the very mechanisms of wear itself. And by understanding where these things come from, we can do something about eliminating it, or at least reducing it drastically. Now, abrasive wear, real straightforward. We have these two moving surfaces. In this case, we see how load is coming down. We have an abrasive surface material coming in between the two surfaces, exceeding sometimes the dynamic thickness of that film strength. Now, there's two types of abrasive wear. There's two-body abrasive wear, and that's usually the lack or absence of a lubricant to separate those two surfaces, or the surface is rough and those asperities are banging up against each other. You can also have three-body wear, where it's an external generated, external ingested particle comes from the outside, dirt, dust, whatever, or it's internally generated particle, a wear particle, or even a product, something from the process. Those things are going to attribute to abrasive wear. And we have adhesive wear. Now, adhesive wear and abrasive wear, usually those two are the number one reasons why a bearing, a gear, a pump, whatever is going to wear out. Those are two of the most popular mechanisms. Now, adhesive wear, that's where we've actually compromised the film strength. So you see we actually have a cold welded area. Those asperities are experiencing extreme pressures, hundreds of thousands of pounds per square inch. Enough pressure to generate enormous amounts of heat. And with that heat, it actually does melt the metal. It cold welds it. We call it cold welding, but it's actually not that cold. It's pretty hot, but it actually welds it. And the interesting thing about welded parts is they actually got pretty strong where the weld line is. Well, that asperity, when it's welded up to another asperity, just isn't going to be strong enough to completely stop that particular componentry from moving. So it breaks off. The weld line stays strong, but the base of those two asperities do break off, and that itself becomes wear-generated debris. And we could also have fatigue wear. Fatigue wear comes in from another hard particle, perhaps from the cold welded particle that broke off, or an external particle coming in from the outside, due to a bad breather or a bad filter, something like that. Anyway, it actually sets up a situation where it's larger than the tolerance between the two surfaces of the componentry. And by doing so, it sets up a bridge between the two, and it actually will set to where that load can actually start to compromise that surface. And when it does so, you set up a microcrack. And when that microcrack occurs, it grows bigger and bigger, it propagates. It starts compromising one of the componentry, if not both. And when that happens, we actually develop a spall. And as that spall develops, we actually start getting parts coming off as well. which then lead to more types of wear debris and so forth. So it's just a situation that accumulates. And the interesting thing about wear failure is that when we do ferrography, which is an analytical examination, obviously, of wear debris, we never just see just one type of wear debris. We see adhesive wear, we see abrasive wear, we see fatigue wear, many different things. Usually a preponderance of maybe one, but there's several different mechanisms at play, because fatigue wear can lead on to abrasive wear. And even we'll explore erosive wear in a minute. Now, rusted corrosion, we're all familiar with rusted corrosion. Rust occurs on iron or iron alloys, and corrosion occurs on pretty much everything. Really, corrosion is a basic definition of corrosion. It's just the oxidation of a metal surface. It doesn't have to be metal, actually. Corrosion can occur on plastic, too. And I guess you could argue the fact that corrosion can occur on wood or anything solid. But the bottom line is it's oxidizing. It's going into a different molecular state. A very common oxidizing agent is water. Well, primarily oxygen. It's really the oxygen that's dissolved in the water that does the oxidation. Water is a great electrolyte. It brings things to the surface, but the oxygen dissolved within the water provides the corrosion or the rust. There's other oxidizing agents as well, things like bleach and wash down chemicals too, and they can actually start oxidizing the metal. Now, when we oxidize iron alloys, it's particularly deleterious because iron oxides don't have malleability and they don't have physical integrity. They slough off. That's not necessarily the case with things like aluminum, other types of white metals, because that oxide layer can actually provide a little bit of a barrier. But with iron, that's not the case at all. It does lose its physical integrity and becomes useless to us, and the surface deforms, and then we have other problems. And cavitation. Cavitation is probably one more mysterious of the things. It's very difficult to start understanding the things that occur on a microscopic level compared to macroscopic. We can think of a bubble exploding, okay? But in cavitation, it's the opposite. We're talking about an air pocket that's actually imploding, and it creates a lot of shock waves. And shock waves that's been calculated up to about 2 million pounds per square inch that can actually blast away on the metal surface. This occurs a lot on pumps, but you know what? It can actually occur on bearings and gear faces as well. It's not uncommon. And unfortunately, a lot of times when we see cavitation wear, we don't really identify it immediately as that. And here's where we actually see bubbles actually form in the line due to pump restriction, line restriction, and a pressure differential that can actually make the bubbles implode. We could have false pseudo cavitation that's coming in from an air leak. It's going to do the same thing. A lot of times people consider cavitation erosive wear because it does break away particles, which actually contribute to more problems. And that brings us to the next thing, erosive, not impact wear. That's where we're actually sandblasting surfaces. This is really dangerous in hydraulic systems where you have servo valves with really tight tolerances. Just blast away at it. And then Brenneling or Brenneling, depending upon what part of the world you're from. Here's where we actually have what's called a plastic deformation on the metal surface. It occurs on bearings. It bends the metal surface and sets up for all kinds of host of problems. Obviously, we want to have the surfaces smooth, but when we have Brenneling and plastic deformation on this, it's not the case. The false Brenneling occurs if you have something sitting on the shelf and there's vibrations, a lot of micro pinning if you occur. That happens too. Now, that's a real quick summation of wear. It's really easy to get our hands around that. And the next thing is the contaminants, particulate, water, fuel, coolant, solvent, oil, things coming in from the outside affecting us, things generated from the internal mechanisms of the componentry that's going to affect things. They're going to have a huge influence. And obviously, particulate has a huge influence on the wear. So does water. But fuel, coolant, and solvent can as well. And solvent, obviously, when things are being washed down and so forth. Oil. Now, oil is contaminant. Now, how's oil a contaminant? It's the wrong oil. You put a hydraulic oil in a turbine, even at 5%, it's going to be an issue. You put engine oil into a gearbox, we're going to have issues. We'll explore that in a minute. And obviously, we're talking about oil condition too and how that can change. Now, contamination, and this is just some quotes. I'm not going to read all these over to you, but the bottom line is where there's Caterpillar, TRW, General Electric, whoever it is, they attribute contamination as being probably one of the biggest things that really has a huge influence on overall equipment reliability. To give you an idea, is a little chart. Particle-induced failures versus non-particle-induced failures. Now, if you take a look at the particular sector, be it transportation, agriculture, mining, all the way down to power gen, you can see where the failures due to abrasion, erosion, fatigue, and so forth are compared. Obviously, particles-induced failure are huge compared to non-particle induced. So that just begs the question, if this is the case, why don't we spend more time thinking about how we can filter out these problems before they even occur? Dealing with breathers, dealing with filters, and so forth. Spending a little bit extra money on filtration, a little bit extra time on these methods that don't introduce particles can have a huge effect on overall reliability. Give you, for instance, on engine life. This is SAE. This is from Society of Automotive Engineers. Relative engine life by having an engine. Now think about this. What kind of micron rating y'all have on your vehicle's engine oil filter? 40 micron, 30, 15, 10, 5. I'll tell you what, you can extend out the life of that engine dramatically by putting in a tighter filter. Now, they're going to cost more, obviously, but an engine costs a lot more than a filter will. This is pretty well known. This is coming in from SKF, and on their website, they actually say lubricant involves 57% of the time. What's inadequate lubrication? Well, it's wrong viscosity, wrong additive structure, acidic, corrosive lubricants, perhaps poor additive health, washed out additives, whatever it is, wrong base stock for the application, incorrect lubrication cycle. So once again, if we start getting a better understanding of lubricants and lubrication, we can get a nice grip on, obviously, how to reduce contamination. And this is where actually oil is a contaminant. Now, we talked about particle ingress, and here's just a really quick little schematic diagram of a hydraulic system. A lot of different ways, at least 7 easy ways in which particulate can get in there and destroy us. It's either built in from maintenance, tank leakage, through the breather, all the way down to dirt on the rods. All kinds of opportunity for things to get in there. Once again, some of this stuff can be eliminated with better filtration and better methodologies. I'll just get a quick examination. I'll use this as an examination of hydraulic systems. Hydraulic systems do require a very clean oil. Oil coming in from the outside, and I know there's a lot of companies out there that spend a lot of time filtering the oil, but they're really demanded to become very, very clean. And keep that in mind too. It's probably not a bad idea to obviously keep that in mind. Lots of different opportunities for residue, be it on the work floor, inside a delivery tank, or left open. Now, one thing I want to make sure that y'all understand too is water and particulate contamination have a huge effect. Now, on one side, you see on the left-hand graph, we have bearing life remaining versus percent water in the oil. You see the reduction in bearing life by just a small percentage of water. It's incredible. But also, same thing holds true for the bearing life in relationship to particle contamination. If you can control water, you can control contamination, you control the livelihood of that particular asset. And we talk about particles, we're really talking about, a lot of times, talking about dust and dirt and sand, which makes up quite a bit. We talk about silica and silicon dioxide is really what we're talking about. It's hard, it's harder than a lot of machine steel, and that's what's going to bring about a lot of wear anyway. Now, we talked a little bit about particulate, talking about water contamination. Water-related problems, corrosion is very understandable. But the thing is, a lot of folks don't realize is that water actually helps oil break down. It's very destructive. There's only a few types of oil that can be adequately mixed with water, and those use the metalworking fluids. And even then, you really have to keep an eye on the chemistry. They always say water and oil don't mix. Well, they don't mix, and they're not friendly with each other either. Water provides an incredible opportunity for the oil to oxidize very quickly. It's a great electrolyte in that respect. It brings a lot of oxygen to within the oil itself. It breaks down the film strength. That's one thing it does. One thing actually water will do on a small scale is obviously starts to emulsify, increases the viscosity of oil. On a very large scale, it will break it down as well and actually decrease. It does contribute to cavitation. It's a leading cause for hydraulic pump cavitation, as well as silting and filter plugging too. So once again, if we can keep things dry, we can have them last longer. We could have it in dissolved water, free water, or emulsified water. In dissolved, we can't actually, up to maybe 400 or 500 parts per million, we won't even be able to see it in the water. We test it, but we can't even see it. You see the free water, that's usually aggregated water molecules floating at the bottom of the tank. Water is obviously denser than oil. It can be emulsified, and that's when it actually looks like the mayonnaise set right there with the huge water molecules. But the bottom line, globules. But the bottom line is any form of water is bad in the system unless it calls for it. And I can only think of a few instances when water and oil should be used together. That's typically in metalworking fluids. Now, This particular study, we take a look at using different types of contaminated systems on how it affects the acid generation. And what's really kind of interesting is that if we take a look at the acid number, acid neutralization number, okay, over operating time. Now, number one, that's clean, dry oil. It isn't until many thousands of hours do we actually start increasing our neutralization number, okay, the total acid number. And that's clean and dry. But if we look at the antithesis, over here, we actually have water and copper, which is it's a nice transition metal, but it acts like a really great catalyst for the whole process of oxidation. That provides us our least opportunistic scenario to where we're going to have that system last any kind of time. All systems, or I shouldn't say all, majority of systems do contain some form of copper or copper alloy in there. And that copper becomes liberated, does act like a catalyst. You put water in there and it's the worst scenario. Lubricants can be formulated with passivating agents to help with that, obviously. But once again, these agents can only take up so much before they become saturated and they lose their ability. Metal and moisture accelerates oxidation. Always remember that. Now, to give you an idea, also, water can contribute to biological growth, loss of dispersancy, and especially in engine oils. And it actually does contribute to chemical reactions, producing slugs and strong acids. It does react with the anti-wear and even extreme pressure agents within the lubricants, too. Remember, these things are polar active. Water's polar, as well as a lot of these surface active agents are polar, as well as the molecules that are found within the oil to do its job too. These things are polar active, and they're going to compete with water, and they're going to react with each other. Now, one particular contaminant a lot of folks never consider as a contaminant is air. Air's a contaminant, whether it's entrained, okay, or if it's in foam or whatever. The bottom line is that does bring down to oil problems. It can affect its viscosity, but it does bring about oxidation as well. Now, air contamination can occur for several reasons. Foaming occurs for several reasons as well. You can have high or low oil levels. The air's churned in by the pump. Turbulent return on the reservoir. Insufficient residence time, which means that oil's not sitting long enough in order to be pumped back in. Air leakage into the system. Grease can actually bring about foaming. A lot of folks don't realize that. A lot of times if you reassemble equipment, a lot of times mechanics he or she will actually use grease to fit the parts together. Well, that can actually, if that's not cleaned out proper, that can actually bring in some foaming. And any change in lubricant's interfacial tension, dirt, chemicals, aging, moisture contamination, all lead to foaming and aeration. There's just a little schematic of what happens on the return line from the suction line and how this can actually take. Now, one particular thing that we don't consider as a contaminant, and it's really unfortunate, but it truly is temperature. Temperature is a contaminant. And I think if we keep that in mind, we realize that as we increase temperature, we increase the reactivity rate. You know, that old Arrhenius rate rule in organic chemistry that some of us learned back in, when we were sophomores in high school, something like that. The bottom line is you increase temperature, you increase reactivity. You decrease temperature, you decrease reactivity. It's the difference between broiling a roast and slow roasting one, or smoking one. When you smoke a piece of meat, you're only keeping the temperature about 180 to maybe 200 over a long period of time. It cooks it. But if you want to cook it quicker, you throw it in the oven and put it up to about 450. It'll cook a lot faster. Well, you're increasing the reactivity of what's going on. Same thing when we do everything else. I mean, if you can keep things cooler, the cooler you keep things, the longer they're going to live. It's just the way it goes. That's why we stick things in refrigerators. Well, that's exactly why we want to put things, temperature control and thermal management on all our lubricated systems. If we can keep the temperature in check, we can reduce the reactivity of particular types of radicals that do establish themselves over time. If we increase the temperature, we increase the water, we increase copper, we're going to break down the oil. We're going to lead to a particular failure mode associated to a lubricated system. This is just known. The last thing, the failure modes associated, we talked about wear, talked about contaminants. But the oil condition, change in viscosity, that leads about, and that could be due to a number of different reasons. And normally, probably, if y'all are familiar with the term Occam's razor, it's a little saying is that usually the simplest explanation is the truest. The bottom line is why would something change viscosity? Well, more times than few, it's because somebody put the wrong oil on top of the oil existing. It's either too thick or too thin. They did a wrong add rate to it. that can bring about a change. The contaminants bring about a change as well. But a viscosity change in a lubricated system will, in fact, cause the system to fail. Acid generation, as these molecules break down, they become acidic in nature and then reform and polymerize. But acid generation will obviously bring about failure. Not only does it affect the additive chemistry in these lubricants, it can actually start breaking down the base oil, and it starts affecting the surface on the componentry too. Oxidation, obviously we see that in forms of sludge and so forth. Sulfation, we see that with, not so much nowadays with the low sulfur fuels, but there is still sulfur in some products, and that can bring about sulfation, which is a form of oxidation. And nitration. Nitration it's in the same family. It usually has to do with the thermal management as well, and creating nitric acids, and that does bring about. And all these things do bring about what's called polymerization, which is we're taking these molecules and we're assembling them into huge macromolecules. Sludge is a form of polymerization. A lot of times, if you actually have an engine that gets in contact with water and glycol or a coolant system under the right heat and pressure conditions, you can actually make one heck of a good solid, and it sets up the piston and fail an engine. It's all about polymerization. Now, one thing, and it's something to always consider too, is that mixing greases can actually lead to failure, as well as mixing oils. The basic reason is that some base oils are not compatible. They have different viscosities, and that sets up for a different grease system. The consistency and grade changes can also bring about problems, but incompatible thickeners. And just go forward, just think that this, regardless of people say if thickeners are compatible or not, just assume they're not, and go forward, because unless you go put this in some serious expensive testing, you're not going to be able to really figure if these thickeners are compatible or not. They can either soften and liquefy and pour out, or they can actually harden in certain cases. It's not very common, but it does happen. I've seen it. These additives compete with each other, be it in oil or in greases. Different companies use different chemistries, and they do compete with each other. It's a really balancing act. And the oil can, if you mix these things together, oils can separate out. Now, base oil differences, if they're incompatible base oils, different viscosities, they can even have different seal compatibility as well. Added differences, well, if you mix oils or greases, you could bring about foaming, loss of demilsability, rust and corrosion, sludge, inadequate wear protection, overheating, accelerated degradation. Why? Because these particular molecules are always competing to do something. And if you put in different chemistries in there, if the research and development hasn't been carried out fully, you're going to have deleterious effects. And what's going to happen is you're going to have competing reactions, and they're not going to want to do what they're supposed to do. They're going to go with where they're going to go, and you're going to lead to all these different problems. You really don't want to mix oils or greases. Hey, listen, that about, we hit right at the 40-minute mark. I want to thank you very much for listening today. I certainly do appreciate it. If you have any questions, feel free to chime in, ask, type away.
Yes, thank you, Michael. We're going to go ahead and open it up for questions. Please feel free to use your chat box, ask a question, or even the raise the hand feature if you want to ask your question directly to Michael at this time. We'll go ahead and give everyone a few moments. While are putting all those questions together, I do want to just thank everyone for attending today on this webinar Wednesday. We have recorded this webinar, and we'll be posting it on our YouTube channel. You can just search ALS Limited to find our channel and then click on the North America playlist. We post not only our webinar Wednesdays, but other video resources there as well. You can also follow us on LinkedIn. We will post this webinar and other valuable resources there on our social media pages as well. We'll go ahead and give it a few more moments. I do not have any questions at this time, but we will keep it open.
One thing too, please feel free to take down my email address too. Shoot me over an email anytime you want if you got any ideas or questions or comments or anything like that. I don't know, Kelly, unless they must have been awful thorough or they bored the heck out of these folks. I think we did pretty good. I don't know if anyone's got any questions.
I have a few comments coming in, but they're just saying they don't have any additional questions at this time, so which is very considerate.
Make sure you all fill out the survey. We're always trying to improve upon everything we do. It's all about, and we're trying to embrace the concept of reliability-centered maintenance, which means don't fail the same way twice going forward. So if anything, if you found anything objectionable or you wanted to see if there's any way we can improve upon it, I'd be really interested in hearing those comments. And also, like, obviously, good stuff too, because that always feeds my huge ego. But I really am interested to see how we can make these 30, 40-minute webinars informative and useful to you guys going forward. Always want your feedback.
Yep, just a few more thank yous, and they appreciate the material covered today. So it looks like we don't have any additional questions at this time. Again, yeah, feel free to email Michael Holloway directly if you have any follow-up questions about this webinar. Again, thank you for attending, and I want to have everyone enjoy the rest of their week. Thanks so much.